Hey everyone, Morgan here. So today we're going to be talking about bond energy. And the question always comes up about where energy is stored. Do molecules have gas tanks, etc.? The answer is energy is stored in chemical bonds. So what we're going to do is try and develop the understanding that when you want to break a bond, it takes energy. You're pulling them apart. Breaking bonds requires energy. And then when bonds form, energy is released. We talked about that previously with just the idea that if you have two things bonded together and you want to break it, you got to pull it apart. Requires energy. Now when they come together, that energy is released. That's because the two atoms or more, really we're just talking about single bonds between atoms. When you have those atoms come together, it's because they're more stable when they're together than when they are apart. Okay? We're going to use this concept to actually calculate the energy of some different bonds, also using Hess's law and the ideas of heat of formation. Okay, now let's imagine the molecule methane, CH4. It is a carbon with bonds to 4 hydrogens. And I think it's a pretty safe assumption that all of those bonds are identical to each other, that it would not take more energy to break this one than that one, or vice versa, etc. Okay? So what we want to do is we want to come up with a reaction where CH4 gas, these are all defined in the gas phase, turns into carbon gas and 4H gas. We just want to break those bonds. We want to pull them apart. We don't want to let anything else form. We don't want energy changes. We just want to know the energy to break those bonds. Now, I have given that kind of a stupid name, but you'll remember it. I call it delta H naught kaboom. We are just blowing that molecule up. Okay? Now, I have some information here that could be helpful. This first one is actually the heat of formation for methane. I'm going to reverse that because I want methane as a reactant. CH4 gas gives us carbon graphite and 2H2 gas, and my delta H naught for that is positive 74.85 kilojoules. Now, it's not my answer, but it's a start. I've got graphite and I don't want graphite. I want carbon gas. So what I'm going to do is I'm going to use this second equation, which is the heat of formation for carbon gas, or sometimes called the enthalpy of sublimation for graphite. Okay, so I'll take carbon graphite becomes carbon gas, and the delta H naught is 718.38 kilojoules. Takes a lot of energy. Now, to get rid of the H2 gas, I've got this 1/2 H2 gas, 1/2 H2 gas to H gas. We could call that actually the bond energy for an H to H bond, and that's 217.94 kilojoules. But it doesn't balance. See, I need to multiply this by 4, which means I'm going to multiply this by 4. Now, 4 times that is a 2, which cancels that. Carbon graphite cancels carbon graphite. And when I add the whole thing up, I get CH4 gas, gives me carbon gas and 4H gas. And when I add up the whole delta H, I get 1665 kilojoules, which is not our answer. Okay? See, when I did this, I broke all 4 of those bonds. So assuming they are all the same, I'm going to divide by 4, round it off, and get about 416 kilojoules. Okay? And that is per mole of the bonds, if you want to think of it that way. Okay. That's now a number that I have established, and I can use it to do some other calculations. I'm going to get interested in this molecule because I want a carbon-to-carbon single bond. Now this tells me the heat of formation of ethane is negative 84.7. I need to be able to write that equation. Heat of formation. Carbon graphite plus H2 gas gives me C2H6 gas. I need to put a 2 there. I need to put a 3 there because that's the definition. Heat of formation energy released when 1 mole of a substance is formed from its elements in their natural states, negative 84.7 kilojoules. Now, to blow up this whole molecule and break every bond, the reaction would be C2H6 gas goes to 2 carbon gas and 6 H gas. Delta H naught, kaboom, is our question mark. So, to get there, what can I do? Well, I can take this heat of formation and reverse it. C2H6 gas gives me 2 carbon graphite and 3 H2 gas. The negative becomes a positive. Delta H naught is 84.7. Make sure my decimal point's obvious. Kilojoules. Now to get rid of the carbon graphite, I'll just come back up to the top there and I'll use carbon graphite goes to carbon gas. The delta H naught was 718.38 kilojoules, but I need to multiply it by 2, so I'll multiply that by 2. And then I need to have the 1/2 H2 gas gives me H gas 217.94 kilojoules, and I'm going to have to multiply that by 6. 6 times 1/2 is 3, so those cancel. 2 carbon graphite cancels 2 carbon graphite. I'm left with C2H6 gas to give me 2 carbon gas and 6 H gas, and the delta H naught for this bigger number, 2829 kilojoules. Now, again, that's not the answer. I have to subtract 6 times 416 because that would account for the 6 carbon to hydrogen bonds that are there, and that's going to give me 333 kilojoules. There we go. All right. So that's page 14. Tune back into the next one, and we will continue this same topic.